To recap, we've said that there is a function, psi, which is a function of the position and the time, that describes our particle, and that we can know something about the observable properties of that particle by operating on the wave function and getting something about the observable back again. So this type of problem, where an operation on a function gives me a number times that function back again, is what's called an eigenvalue problem. And if I have a function that solves this equation, then the function is called an eigenfunction of the operator. And the value that I get is called the eigenvalue for that operator when it acts on the function psi. So if psi is an eigenfunction of this operator O hat, and it has an eigenvalue O, then what this means, the way we interpret this, is that if we measure the property that's associated with this operator for the system that's described by this wave function, then we will always, for every time we make that measurement, we will always get the value O. And so there's no variability, there's no uncertainty in our value for O. So we know exactly what the value of that observable is if the wave function that we're describing our system with is an eigenfunction of the operator. So this means that we have some choices to make. So we could imagine solving an equation where we know exactly what the position is. So if we found psi that solved this equation, we would know x exactly, which means that any other operator that operates on psi, which is not an eigenfunction of that operator, we won't know exactly what that value of that observable is. So we could imagine operating with some operator that gives us the total energy for the system. And then we would find, if we find these functions that solve this equation, we would know total energy exactly. Or we might choose to know the momentum exactly. As it turns out, what we decide to do, because it makes the most sense, is to know the energy of our system exactly. And so the equation that we want to solve is this one. We want to know what the energy of our system is. So remember that total energy is kinetic energy plus potential energy. So our total energy operator, which we give the symbol H for the Hamiltonian, is the kinetic energy operator plus the potential energy operator. And so that is just minus h bar squared over 2m. Take the second derivative and then multiply the wave function by whatever the potential energy is for that system. So that's our total energy operator. Now, in general, our wave functions are time dependent. That is, the particle is not staying in one place or staying at one momentum all the time. It doesn't always have the same kinetic energy and the same potential energy. It's evolving over time. And so if we want to include the time dependence, the equation that we're going to solve is that the time dependence, which we get from operating I h bar, take the derivative with respect to time, so how it evolves in time, has to be equal to the total energy operator operating on psi. So this is the full time-dependent Schrodinger equation that I need to solve. So if I can solve this, and notice it's a differential equation, when I solve it, I'm going to get functions. So solving a differential equation gives you functions. So it's going to give me the functions psi that solve this equation. And that's what I'm after. I'm after the wave functions that satisfy the conditions for the total energy of the system. So in general, there are differential equations which we call separable. And what we mean by that is that this wave function that we're after is a function of the position, I'm just going to say r, so x, y, and z, and the time. And I could write this as a wave function that depends only on position and multiplied by a wave function that depends only on the time. So if my equation is separable, then my actual function is just a product of two functions, one in the position and one in the time. And for conservative forces, all of the forces that act on our particles are called conservative forces. This will always be true. We can always separate these variables. And what's nice about this is that this allows us then to write an equation that just has to do with the time, and then write an equation that just has to do with the position. So let's see how that works. So if I operate I h bar, take the first derivative with respect to time on the position function times the time function, and then that's equal to minus h bar squared over 2m times a second derivative of position operating on my wave function, plus take the potential and operate on my wave function. You'll notice that this partial derivative only acts on the time part of this, and this partial derivative only acts on the position time part. And so what I end up with is I h bar for the partial with respect to time. The position part of this is a constant. So I'm just taking the partial of the time part of this, and that equals minus h bar squared over 2m del squared psi r plus v hat psi r, and that whole thing is multiplied by my time part of the equation, because this partial derivative only acts on the position part, and the time part is a constant when I take this derivative. So it just is a constant out here. And these are just multiplied together, and so I can factor out the time part of my equation. So now if I divide through both sides by psi at rt, so the whole thing, right? I'm going to end up, so when we divide by the total wave function, we can see that over here on the left-hand side, that our position wave function cancels out, and that over here, the position wave function is going to cancel out with this, and both of these are going to cancel out over here. And so I can write then that I h bar over phi at t times the derivative of phi at t with respect to t is equal to minus h bar squared over 2m del squared psi at r divided by psi at r plus v hat. So I can see now that I have this side, which depends only on the time, and this side that depends only on the position. And so if those two things equal each other, then they have to both be equal to a constant. Because if I change the time, I don't change this. And if I change the position, I don't change the left-hand side. And so they have to be equal, and they have to be equal for all time and all position, and that means they have to be equal to a constant. So I can write that I h bar over phi at t, d phi at t dt is equal to constant E, my total energy, and minus h bar squared over 2m psi at r, del squared psi at r, plus v hat is also equal to the total energy. So now if I multiply through on this equation by phi at t and multiply through on this equation by psi at r, I get two differential equations. I h bar, take the derivative with respect to time, is equal to E times phi at t, and minus h bar squared over 2m del squared psi at r plus v psi at r equals E psi at r. And so I have separated my time and position dependent into a time dependent differential equation and a position dependent differential equation. And the time solution is pretty easy to do and is always the same for every wave function. So we'll see what that is. The solutions to this position dependent one, these psi at r, are called the stationary states of the system because they don't depend on the time. So the time-dependent wave functions, phi at t, that solve this equation are e to the minus I e times time over h bar. And those, you can plug this back in, so you can take the derivative and plug this back in and show that these equations, in fact, solve this equation with an energy E. So E over h bar is equal to the frequency. So how do I know that? Well, I know that for a wave, E is equal to h times nu. And h bar, remember, is h divided by 2 pi. So if I take this, E equals h divided by 2 pi in order to get h bar, then I have to multiply by 2 pi times the frequency, and that is the thing that we call omega. So omega is just 2 pi times the frequency, so we incorporate that factor of 2 pi in. And then h over 2 pi is h bar. So E is equal to h nu, which is equal to h bar omega. And so E divided by h bar is equal to omega. So I can write these as e to the minus I omega t. And so you can see that this time-dependent function tells us about the frequency of that wave. So the spatial part of this wave function, psi at r, is given by this Hamiltonian equation. So we had said that the Hamiltonian is the kinetic energy operator plus the potential energy operator. And so if I operate h on psi, I get h bar squared over 2m del squared psi plus v hat psi and it's an eigenvalue problem. We're going to insist that we know the total energy exactly, and so that's equal to E psi. So in shorthand, we could write that H hat psi is equal to E psi, and it's this spatial part of the function that we're going to focus on in this course. We know what the time dependence looks like. What changes for each of our systems is the spatial part, and it changes because the forces acting on the particle change, and the forces acting on the particle is what dictates what this potential energy is. So each system, every system that we look at, has different forces acting on the particle, so different potential energy. So our Hamiltonian equation is slightly different because we have a different potential energy, which gives us different wave functions for each of our systems depending on what forces are acting on the particle.